lecture on partial derivatives and error estimates. This is the first lecture on the topic, and today we'll be mostly talking about the significance of the topic, looking at various real-life examples, particularly from medicine. And we will see how a bigger phenomenon that depends on many smaller processes underlying the system undergoes a change, no matter how small or how big it is, based on even the tiniest, the micro change that occurs in one or more of the underlying processes. And then we'll gradually move towards understanding the errors, how we can estimate them, and we will also learn about the reverse engineering that sometimes work best to understand a bigger change and the smaller change, the small errors that we need to estimate. So let's go ahead.
We regularly measure blood pressure of people with hypertension. We do that to observe the effect of different foods or moods, exercise or drugs or stress on their blood flow. This is very important for a good quality of their lives. A small change in their food or missing a drug dose or a financial stress might shoot their blood pressure to a level that could be fatal for them. Another good example could be of flooding. If you have flooding in your area at some point of the year, you must know that it could be due to many factors. It could be the location of your area, the geology, the state of ground conditions, could be drainage problem, the catchment size, vegetation, or it could just be the malmanagement.
So if we call the bigger phenomenon as big F, and it depends on many small underlying processes, we call them x1, x2, up to xn mathematically, then we can express the dependency of F on all these variables in terms of a combination of those variables. There could be independent terms which depend individually on x1, x2, up to xn in different ways. There could be different functions of the variable, or there could be the products of the variables involved. In any way, it will be a function of x1, x2, up to all variables xn involved. So if there's a time for change, then there's a time to look at the change that may be occurring at x1 or maybe at x2 or any of the variables up to the variables we have defined. To observe changes in physical processes, we need to form their mathematical models. Mathematical models are mathematical functions that can be expressed in terms of their underlying variables, like we saw in the previous example. And we know that these mathematical functions are differentiable functions in mathematical terms because they are undergoing changes. And differentiable functions are continuous functions. So let's start by observing continuous functions, how they look like. We know that there must be no breaks or cusps in them, and they should be smoothly growing or decaying, as we can see in these examples. F of t defined by 3 times t is a linear function, has no breaks or cusps. It's a continuous function in the given domain. Similarly, the function g defined by t to the 4 is continuous in its given domain. The function h of t, which is an exponential of t, and the function k of t, which is sine of t, they are also continuous functions. And if these functions are continuous, then any composition of these functions will also be a continuous function. So for example, if we construct a function f, big F of xy, which is defined by the product of fg plus the product of h and k, then it is a composition of continuous functions, so it is itself a continuous function. And we define it by 3x y to the 4 plus e to the x sine y, as we have defined the functions f, g, h, and k.
When we talk about partial differentiation, we consider a simpler function. So let's consider a simpler function of x and y defined by x squared plus y squared. And since f of xy is a combination of two functions of x and y which become one function, we name it a single variable z. And the figure shows how it looks like. Okay, so we observe the rate of change of this function at a certain point where x is 1 and y is minus 1.
Now, without naming x and y, we don't know what x and y are. We're just looking at the big picture, that we want to see the change in the big picture, and for that we want to observe the change at a particular point where x is 1 and y is -1. And this is what we mean by looking at the rate of change of f at the point 1 and -1, that we want to know how a change in x or a change in y would affect the change of the function f, which is depending on x and y.
Initially, we start with a simpler way to deal with this problem. So we fix one variable. So for example, we choose x to be fixed and we fix it to be x equal to 1. In this way, our function z becomes 1 plus y squared. Now z is depending now only on one variable. We have already fixed x, and now we want to see what change would come to z if we just change y. So let's look at the worksheet and see how it works. Graphically, we are looking at the surface x squared plus y squared where x is fixed to be 1, which means that we are looking at the curve z equals 1 plus y squared, which must lie on a plane because it's a curve. It's a parabola. So let's look at the plane x equal to 1, and we see that the parabola 1 plus y squared is on this plane, which is crossing the surface x squared plus y squared at x equal to 1. And now when we consider the partial differentiation, which in this case could be taken as a total differentiation because there is only one variable out there which z depends on. So the change in z with respect to y, which is written by partial z by partial y, can also be considered as the total change in z with respect to y because no other variable is present. And we know that this would be 2 of y, and since there was a condition to consider y as -1, at this point, dz by dy or partial z by partial y becomes -2. For a deeper understanding, we consider the basic definition of change, which you know very well. It's only that we are considering a partial change, so we will observe the basic definition with respect to one variable only, so that we are able to differentiate each function with respect to one variable, keeping the other variable constant ahead. So we are considering f as a function of x and y, a generalized function of x and y, and we see that if we are considering the change in f with respect to the variable x, then we have to apply the basic definition. Sometimes it is also called the first principle to only x here because we are observing the change with respect to x. So when we apply the limit, then we add a small increment h only to x, not on y, keeping y as a constant variable, which has a constant value. The rest is the same that you have already seen in considering the differentiation or the derivative of a dependent function with respect to an independent function, that we add the increment to x and then subtract the function f of x plus h y by subtract the function f of xy from the function where x is replaced by x plus h. And then we divide the difference by h as before. And similarly, when we differentiate f with respect to y, we keep x as constant and bring in the increment to the variable y only. And then subtract the difference of f of x with y plus h and f of xy by h. To apply the idea, we consider the previous example x squared plus y squared as the value of z that describes the surface z equals x squared plus y squared mathematically. And we know that if we differentiate with respect to y, keeping x constant, then the differential would be 2y. We are interested to apply excuse me, the basic definition on partial f by partial y. And we know that we only put in an increment on y in this case. So when we do that, we come down to an expression where f of x y plus h minus f of x y becomes x squared plus y plus h squared, and then minus x squared plus y squared.
we know that the terms x squared and y squared will be cancelled out, and we'll be left with 2yh plus h squared over h, which we apply the limit on. But we still see that before applying the limit, we can factor out h from the terms 2yh plus h squared, and that factor of h will be cancelled by the h at the bottom, and we'll be left with 2y plus h, which is a much simpler expression, and when we apply the limit on that, we get 2y as before. Now when we look at the slope of the above tangent line, because we know that partial f by partial y would be the slope of the tangent at the surface x squared plus y squared, where x equals 1, and partial f by partial y would be simply excuse me, df by dy. So it will be the slope of the tangent to the curve 1 plus y squared, or to the surface x squared plus y squared, where x equals 1. So when this slope turns out to be 2y, and we know that when y is minus 1, the slope turns out to be minus 2. We see that the slope of the tangent to the curve 1 plus y squared at y equal to minus 1 turns out to be negative.
For workout purposes, we mostly rely on direct solution. There's no need to apply the basic definition everywhere. It was barely for your deeper understanding, so you can see what's going on behind the scene. So in direct solution, we are considering a function r of xy, which is defined by x cubed y plus 2x squared y4. Now, please grab a pen and paper and differentiate r with respect to x. So find out partial r by partial x, which means that you will be differentiating both of the terms x cubed y and 2x squared y4 with respect to x. Please do that by pausing the video and then compare your answer with mine. And now I want you to note what happens to rx, r sub x, which means partial r by partial x, when x is 0. We note that both of the terms have x, and when x is 0, the change in r with respect to x turns out to be 0. What does that mean? There's no change in r if x changes. And next, we look at the same function by differentiating it with respect to y. So ry, r sub y, which is partial r by partial y, turns out to be x cubed plus 8x squared y cubed. And now you can see that ry or r sub y does not vanish if y is 0, because y is present in one term only, not in x cubed. So when y is 0, x cubed remains there. So we have observed a function which was depending on x and y in a way that if we change x and then we insert the value of x equal to 0 in the change turns out to be 0, which means no change at x equal to 0. However, it does undergo a change when we differentiate it with respect to y. When the variable y changes, the change in r is such that if y equals 0, then ry only depends on x cubed. So it still has a value of x cubed. It does not vanish at all.
You get a bit more challenging example where the function f of xy is a combination of 3 times e to the xy cube times sine y. Now we know that here we are having a product of two functions, e to the xy cube and sine y, while 3 is a constant. So when we differentiate it with respect to x, we consider both functions if they have x, and we see that x is there only in the exponential function, not in the other function. So we differentiate e to the xy cube with respect to x and keep sine y as constant. And when we differentiate e to the xy cube with respect to x, we know that it will be e to the xy cube times the differential of xy cube by the application of
The chain rule, you're right. Okay, great. So when we consider the differentiation of f with respect to y, we know that y is present in both of the terms, e to the xy cube and sine y. So we will apply the product rule, and we will first differentiate the first term, e to the xy cube, with respect to y, keeping sine y as constant, and then we differentiate sine y with respect to y, keeping e to the xy cube as a constant. And then we apply the differentials as before. The first term has e to the xy cube differentiated to 3xy squared times e to the xy cube by the application of the chain rule times sine y. And then in the second term, we simply have to differentiate sine y with respect to y, which is cos y. Now, if you look at both terms, you see that e to the xy cube is another common factor other than the constant 3. So we take both of these guys out, and inside we are left with 3xy squared times sine y from the first term and cos y from the second term.
Once we know how to take partial derivatives, we can easily take second order partial derivatives or the double derivatives, double partial derivatives, which means that if there's a function f and we are taking partial squared f by partial x squared, then we are differentiating f with respect to x twice. Similarly, by taking partial squared f by partial y squared, we are differentiating f with respect to y twice. More important thing is to understand the mixed derivatives, which means that we are differentiating the same function with respect to x first and then with respect to y, or with respect to y first and then with respect to x. In the first case, when we take partial squared f by partial x partial y, we are differentiating f with respect to y first, and then we differentiate the whole thing, partial f by partial y, with respect to x. Conversely, by taking partial squared f by partial y partial x, we are taking partial f by partial x first, and then we differentiate this with respect to y. Now, there is a very well-known, very important theorem called the mixed derivative rule, which says that it does not matter which order you take while taking the mixed derivative. And now we observe the function we formed from a composition of 4 functions before. fxy equals 3 times x times y to the 4 plus e to the x sine y. And we see that the first derivative turns out to be 3y4 plus e to the x sine y, because the first term was linear in x, so it disappeared. And the second term has an exponential function of x, which stays the same. And in fy, you have 12xy cube plus e to the x cos y. Now, in all these expressions, the graph that represents these functions must be involving some polynomial functions and exponential functions and sinusoidal functions all combined together. And we are going to see that. We also note that in f and fx, if y is 0, the expression turns out to be 0. So we must see a flatter curve along y equal to 0. However, this is not the case in fy, because y equal to 0 would generate cos of y equal to 1, and the first term only will be a 0 term, and the overall expression for f of y would be e to the x at y equal to 0. So we must see an exponential curve. In the second derivatives, we see that f of f double x would not disappear, now would be equal to 0 at y equal to 0. However, fyx, which you note that is equal to f of xy, would again show an exponential curve along y equal to 0. Let's observe this in the graphical view. This is a 3D view of our f, and you can observe it from all sides. This is a graph of partial by partial x, which has turned all the corners up, and that is the effect of the change in x. And it also shows a flatter surface along y equal to 0, which is clearly shown in partial f by partial x, because y equal to 0 makes it 0. And here is partial f by partial y. And you can observe that along y equals 0, it is simply an exponential curve of x along y equal to 0. And that's what our double derivative or the mixed derivative look like. Partial square f by partial x partial y. And here you can observe that along y equal to 0, again the curve looks like an exponential curve. In the next lecture, part 2 of lecture 1, we'll be talking about upper bounds on partial derivatives that will help us understand the foundation of the connection between errors in independent variables which lead to the errors in dependent variables. So stay tuned and subscribe to the channel to get the notification at the right time for the upcoming lectures in the pipeline.